So hello everyone. I'm Tang Wei, and today I'm going to talk about something related to Ethereum virtual machine. Just short introduction about myself. I'm a Rust developer working at Parity Technologies, and I was the author of the SputnikVM, which was a VM designed for Ethereum Classic. I worked on Parity Ethereum, and now I work on the Parity Shasper, which is our Ethereum 2.0 implementation. And I was involved in the Constantinople hard fork. If you remember, I was the author of the infamous 1283 EIP, which caused like 4 months of delay for the hard fork. So for this talk, I basically just want to give like a quick introduction about Ethereum virtual machine in case you are not familiar with it. And I also want to discuss something I found really fun when I initially got acquainted with Ethereum virtual machine, and also something that I think most developers and also the Ethereum communities are found really miserable about Ethereum virtual machine, and how I think we can do something about them. So for Ethereum virtual machine, it's basically like a really simple stack-based virtual machine. It's a little bit different from RACV or our like the existing x86 CPUs. So what we have, so those are register-based machine, but here we have a stack-based virtual machine, which basically means we have a stack, and all the operations are executed based on the stack. So for example, we have some simple operations such as we need to put some value into the stack, or duplicate a value on the stack, or swap some values on the stack, and some arithmetic operations, comparison operations, bitwise logic. Also some stack memory storage flow control. That is all the basic thing you will have for stack-based virtual machine. But for EVM, because we want to interact with the block, and also with our account, with all the other information, so we have some environmental information, opcodes. We also have some logging opcodes. We have some system operations. The system operation is kind of really big. Like we have some opcodes that will take like seven stack items and do some really crazy stuff, and then push one stack back. So some really fun things. So this is about like data and code. So for Ethereum virtual machine, when you first deploy a contract, what you have is you do a contract creation transaction. So the code you provided into the contract creation transaction is a little bit different from the actual runtime code you see on the blockchain. So it's a runtime with a preamble. So you have a preamble that says, I want to push the code below as a return value. So for this execution, and then this transaction will then interpret this result of the execution as the code, and then deploy it onto the blockchain. So for contract code is the return value of the contract creation transaction. And then when you actually call a contract, you only execute the runtime code. So we actually have two different kind of code here. And the interesting thing here is that there's actually a process when we treat data as code. So the return value, which is actually should be usually interpreted as data, is used as code for the deployment. So that is kind of an unusual choice, because for most VMs, you actually want to separate data and code to make sure we always make sure we don't mess things up, especially for something like a blockchain. So with this, you can actually implement something like EVAL, which basically allows you to execute any data as code on the blockchain. So what we do is basically we just get any bytes as a runtime code we want to execute, and then we just directly insert a deployment preamble, and then we just call create a new contract as an internal transaction. After that, we just do a delegate call, so that will just execute that code. This kind of behavior is actively being used in Solidity. If you look into the Solidity code, you will find the generated Solidity code. You will find in the end there will always be something really weird. That is actually a hash of the the Solidity, something like a config file, which Solidity will always put those data at the end of your bytecode. So that is actually a data, but Solidity decided that it may be a good idea to just have it in the end of the bytecode. So it's definitely a trade-off, so you get some flexibility. But on the other hand, especially recently when we want to do some more EVM improvements like EIP 615, it creates some issues. So it really creates some issue for contract verification because actually everything for the deployed contract code is at first interpreted as code. It's just some of the code in the end will never have a chance to be executed, but they do have a chance to be interpreted as code. So in that case, we have some issues with contract verification, and also for the filter. Yeah, this is just I mentioned for the EIP 615 case. And another really interesting thing, this is just a really small thing that I also find really interesting, is a self-destruct opcode. So using this opcode, this is probably really well known among code developers, but I just find like it's still brought up from time to time. For using this opcode, you can actually destroy Ether on Ethereum. So what you do is you just create a contract that has self-destruct, and you self-destruct to the contract itself. So what happens underneath is this opcode will, of course, it will register current account in the destruction list, and it will first increase the destination balance, and then it will set the current account balance to 0. So if you set the destination the same as current account, then it will first increase the current account balance by the balance amount, and then it will set the current balance to 0. So you're effectively destroying some Ether. Yeah, now here comes the misery part. So this part is basically talking about all the past incidents and some of the miseries we had from a core developer's perspective. what we have done, something we have done wrong, and probably how we can improve in the future. So the first EIP that probably caused a lot of issues lately is the EIP 161, which is a state try clearing. So this looks like a fairly good EIP from the beginning. We basically, because at that time we had a denial of service attack, and we have a bloat of like use this account created onto the blockchain, and we want to get them deleted. So we have the EIP 161, and what we do is we define a new status for our account, basically called empty. Our account is called empty if it has no code, zero nonce and zero balance. That seems pretty workable. And if we have an empty account, then we do certain operations to delete that account at the end of the block. However, the issue is that we also have another definition, which is if the account doesn't exist. We also have a definition that the account actually exists. It's kind of empty. It has no code, zero nonce, zero balance, but it also has zero storage. So it's kind of like we have a lot of different definitions for this. And in the code, we need to handle each of those cases separately. So this is kind of like become an issue lately. For example, the earliest issue we have is RIP EMD precompiled, which if you look into the Go Ethereum code, you will find there is just a special case for the state try cleaning code that about the RIP EMD. And the latest one we have is probably the 1052, which was part of the Constantinople. We nearly had a consensus split on the Robeson testnet, and really it's really fortunate that we avoided that, so it didn't cause more delays. The issue, I think, is mostly from a specification perspective, that because now we have different account status. Account can be empty or can be non-existent. Those things actually must be specified in any specification that deals with the account. So in the beginning, the 1052 only has a specification about an account being non-existent, but it doesn't have the explicit case for account being empty. So that was kind of the cause for this issue. So if right now if you review any EIPs, and if you say EIP have a condition about an account being non-existent, but it doesn't have the condition about the account being empty, it's probably missing that part. And then we have another misery, which is 1283, which deals with account storage. So the incentive is pretty simple. So we have a lot of complaints that the SS store gas cost is just too high. So some contracts want to use the SS store to do some certain operations, like making it a lock or using it to pass some information between call frame. And under current gas scheme, it just costs too much gas to do that. So that's the basic incentive. So the gas cost is too high, so let's decrease it. What could go wrong? Turns out we have a re-entry attack. The issue is we have a gas stipend, which is at 300, and because we reduce the gas cost from 20,000 or 5,000 to 200 for some cases. The issue is sometimes previously it's impossible to call iStore purely using gas stipend, but now you can. So that's the first issue. This is kind of the 1283 is kind of first of its kind to do a decrement of gas cost, and there's a lot of arguments about what actually went wrong, and I think the general consensus at the time was that if we do a decrement of gas cost, it sometimes can be unsafe. So, okay, we talk about decrement of gas cost. And there comes a new EIP, which is EIP 1884, which is a EIP that is going to be included in Istanbul. And it also, this EIP is also a relatively simple gas change. And it has a really fairly some other objective. But one of the objective is that we are dealing with another opcode, which is islord, which reads a value from the storage. And the objective is really simple. The islord gas cost is too low, so let's just increase it. What could go wrong? Turns out, in this case, we might prevent some contracts from functioning. So the issue is still kind of related to gas stipend. So previously, we only need 200 gas costs for the islord, and some contracts are happily using islord opcodes, just purely relying on the gas stipend. But now, increasing this to 800, some of these contracts will just run out of gas for using the gas stipend. So we found out some recently deployed contracts that will be not functioning under the new gas scheme under 884. And there are also other issues, which there's a really great analysis provided by Martin. If you want to look, here it is. So now we have a case where increasing a gas can also be unsafe. So yeah, so this is kind of a quite bad situation for us, because we just want to, sometimes we need to change the gas cost. Either we want to just to make it adjusted with the actual real cost when do blockchain execution. But it turns out that doing any gas cost change will require a lot of work than we previously thought. So some futures. So just this is just some thoughts I have about how maybe we can get off our misery. So the basic thing I was thinking is that if we are redesigning EVM today, what we may be able to do to get things slightly better. This is purely, some of them are new research, so I haven't got any review from peers, so take it with a grain of salt. So first of all, so for EVM, we just had too many ways for a contract to fail. So the overall transaction can run out of gas, and also internal call or create opcode can fail. This is okay. It provides flexibility, But in the same time, it really like make security analysis harder for those contracts, because for each call you must check that whether this call has succeeded or failed, and if you miss any of them, then or any subsequent contract misses any of them, then this execution may be unsafe. I think this is an issue with dealing with exceptions. So in most other like VM, like WebAssembly, you have a specific operation called trap. When a trap happens, you just exit the current VM execution. So maybe we can change the out of gas exception in EVM to be a trap. That is, it should hold the full transaction and revert any state change. And then for usability, some contracts should use return cone to signal whether the operation, non-fatal operations, is successful or failed. And then there come the gas cost. So that is, from the last section, that is actually the biggest misery we have. So the issue is kind of with something we have the Herm's law, which states that anything, I don't remember the exact code, but basically states that anything you exposed to developers, no matter whether intentional or unintentional, those developers will make assumption of it. So that's kind of our issue here, because we have developers who make assumptions about the gas stipend or about a specific opcode, gas cost, which in the future is still subject to change. And that is kind of not really what we want. So a really simple fix we may have is just to remove those exposed information from EVM. For example, we just remove the gas opcode from the VM, and I don't think. And if we combine it with the previous section that makes out of gas always trap, then it shouldn't actually break a lot of contracts. So if we don't want developers to make assumptions on gas costs, we shouldn't allow this information to be exposed. And in this way, we actually make the gas cost, all the gas cost calculation we have are purely implementation detail. So the EVM cannot query this information, and in that case, we will be able to more freely change it to adjust them to make sure that they always have similar actual cost in the real block execution. Yeah, and for the code and data, in some cases, probably in the future, we want to separate them. We either can have separate sections for code and data. This is the direction 615 is taking. Or we add some additional validation step in EVM, and we reject unknown opcodes. So this is the direction. There's an EIP called 7012 is taking. And that's basically it. And that's all. Thank you.
Thank you. Any question for him? Okay, we still have time after that, so please stay here.
Yeah, I'm just Okay, I'm just curious, maybe you can give us some insight why EVM was designed to be a stack-based virtual machine, because like previous talk was about using RISC-V, which is, I believe, like a usual architecture with registers and stuff, so it's probably fine for blockchain, but why is EVM is stack-based?
Different like machine designs, you can either make your machine stack-based or register-based. So RISC-V is a register-based instruction set, and EVM is a stack-based instruction set. There are some, I don't know the exact reason why we have stack-based in the beginning, but we do have some EIP proposals saying maybe we want to like switch to a register-based machine or something, but in most cases they are equivalent. Like
okay. Because I thought that stack-based is something like unusual, because in real life you have a lot of register-based, and stack-based is like something from like force, like something old and strange, and like why would you use it? Or if it's equivalent, then that's fine, I think.
Yeah, and I do think there are other VM that are stack-based that widely used, but I can't remember the name right now.
Thanks.
Thank you.